This video is going to be an introduction to scientific notation. We have 10 problems here, 10 numbers in scientific notation, and they're asking us to write each of them in standard format. Standard format is what you're used to seeing numbers written in, and scientific notation is the new thing we're going to be talking about today. So let's take a look at what each of these numbers has in common in the way that they're written now, which is in scientific notation. So there's some number out front, and then it's multiplied by 10 raised to an exponent. And sometimes that exponent is positive, sometimes that exponent is negative. One thing I want you to notice about this number out front, okay, in number 1 here we have 4.5691. Number 2 has 7.504, 6.068, 1.16, 1. Every time there's only one digit in front of the decimal point. Okay? That is a key component of scientific notation, that there's always exactly one digit in front of the decimal place, and that digit is 1 through 9, because there's never a 0 in front of the decimal place. Number 1 says 4.5691 times 10 to the 5th. Well, let's expand what we know about 10 to the 5th. Raising something to the 5th power means multiplying it by itself 10 times. So this is 10 times 10 times 10 times 10 times 10. I'm going to think about this in terms of order of operations, which tells me that when I have a bunch of things multiplied together, I just work from left to right. So the first thing I'm going to do is multiply 4.5691 times 10. Multiplying by 10 moves the decimal to the right one place. So now we have 45.691 times, and then there's still 4 tens back here. If I multiply by 10 again, multiplying these two together, I get 456.91 times 3 tens. If I continue to do this, I'm going to move the decimal place several more times. In fact, I'm going to move it 3 more times because there are 3 more tens to multiply by. So if I move the decimal place 3 more times, I actually end up with 456,910. So the number 4.5691 times 10 to the 5th, okay, was the scientific notation version of 456,910. So let's try another example here. Number 2 says 7.504 times 10 to the 8th, and we know that that means 7.504 times 10 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 times 10. I think I wrote 8 tens there. 1, 2, 3, 4, 5, 6, 7, 8. Good. And every time that we multiply by 10, it means that we move the decimal place to the right one place. So I take 7.504 and move the decimal place 8 times. I'm going to go 1, 2, 3. I've gone 3 to go past these three digits that are already here, and then I'm going to have to go another 5 places. And I'm going to fill all of those with zeros. So now, if we write this out, we've got 5 zeros back here, and I'm going to put commas in the correct places. So this is 750,400,000. That is equivalent to 7.504 times 10 to the 8th. And I think this example really illustrates why we use scientific notation. In science, especially when we're talking about something like astronomy, or we're describing the size of an atom, we're talking about numbers that have a ton of 0 digits in them. And a shorter way to write those numbers down is with what we call scientific notation, where we move the decimal place until there's one digit in front of the decimal and multiply by 10 to some power to show all those zeros that we sort of took out. I'm going to skip example 3 in this video and go straight to example 4 because I want to talk about what's going to happen now when we have a negative exponent with our 10. Well, we know what to do with negative exponents. We know that that means 1 over that number with the positive exponent. So it's 1 over 10 to the positive 4. Well, that just means 1 over 10 times 10 times 10 times 10. Which means that instead of multiplying 1.16 by 10 4 times, I'm actually dividing it by 10 4 times because it's in the denominator of this fraction. Dividing by 10 moves the decimal place in the other direction. So now I'm going to take 1.16 and I'm going to move the decimal to the left 4 places. I'm going to fill these empty places with zeros. So our answer is 0.000116. Again, we have zeros that are now inserted into the standard format number that were originally represented with our 10 to some power. In this case, though, we moved the decimal place to the left because 10 to the negative 4 told us we were actually dividing by 10 4 times. I'm also going to skip number 5, and we'll go straight to number 6 up here. 6 says 3.5324 times 10 to the negative 6th, which means, as we saw in the last one, that we are really multiplying by 1 over 10 to the 6th, which is another way of saying that we are dividing by 10 to the 6th, which means we're dividing by 10 6 times. So we're going to move our decimal to the left 6 times because we're dividing by 10, which moves our decimal to the left. So our final answer for this one is 0.0000035324. This is another example that really illustrates that it's nice to be able to write this in scientific notation rather than having to make sure you've written the right number of zeros out in that decimal. We're going to switch it up now and go the opposite direction. Now we're given numbers in standard format and we're going to switch them into scientific notation. For number 11 here, we have 56,000. The first thing I notice is that I can think of that as 56 times 1,000. And then in fact, since I want to actually have not 2 digits in front of a decimal place but 1, I want to move that over 1 more. So I want to think about this actually as 5.6 times 10,000. So 5.6 times 10,000, well, we know that 10,000, let's see, we have 4 zeros here, so that is 10 to the 4th power. We can write 5.6 times 10 to the 4th as the scientific notation of 56,000. So I'm going to write that answer up here, 5.6 times 10 to the 4th. I'm going to skip around and do another example where we're going to end up with a positive exponent, and then we'll get back to negative exponents in a minute. So I'm actually going to skip down to number 14, which has 8,097,000. So again, we want to move our decimal place so that only the 8 is in front of the decimal, which means we're going to need to keep the 097. We're going to go to the 7 because we have to go to the last digit that's followed by only zeros. This 0 has to be kept because 8.097 and 8.97 are different numbers. So let's see, how many places have we moved the decimal? 1, 2, 3, 4, 5, 6. We've moved the decimal 6 places, so to compensate for that, we need to say that this is multiplied by 10 to the 6th power. Let's look at 15 before we do one with a negative exponent. In 15, they have 1.9514. It may look like this is already in scientific notation because you don't actually need to move the decimal to have there only be one decimal and one digit in front of the decimal. However, for it to be in correct scientific notation, we do need to indicate that there is a times 10 to some power. Since we don't want to multiply this one by anything, we really want to express that we're multiplying it by 1. Well, 10 to the 0 power is 1. So really, to put that in official scientific notation, we'd need to write that as times 10 to the 0 power. Let's try number 12 now. The reason I haven't done this one up until now is because I know it's going to have a negative exponent with the 10, because we have a decimal that is less than 1. So in this case, we need to move the decimal to the right 3 spaces to get one non-zero digit in front of the decimal. So we'll have 1.4268. And how many times did we move the decimal? Well, we moved it 3 times. But because we moved it 3 times to the right to get 1.4268, in order to get back to standard form, we'd have to divide by 10 3 times, okay, which means that we need to write a negative 3 as our exponent for the 10. So this comes out to 1.4268 times 10 to the negative 3. Number 13 is similar to number 12, except that we have a lot more zeros to deal with this time. So I'm not going to copy down the whole number because I would probably copy down the number of zeros incorrectly, so I'm going to draw from up here on the original number. 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then I need to go in ninth place to get the decimal behind a non-zero digit. So we moved it a total of 9 places to get to 2.67, and I moved it 9 places to the right, which means that 2.67 is 10 to the 9th times bigger than the original number. So to get back to the original number, I would need to divide by 10 9 times, which means I need to multiply 2.67 times 10 to the negative 9th. We'll do number 16 here. We're going to need to move the decimal place 1, 2, 3, 4, 5, 6, 7 places to go behind the 5. Then we'll need to keep this 5.009. Remember, those zeros need to stay there. We moved the decimal place 7 spaces, and we had a number much smaller than 1, so we need to have 10 to the negative 7th as our 10 to the power portion of our scientific notation answer. The last thing I'm going to do is questions 18 and 19, so I'm going to skip 17, we'll do 18 and 19, then I'm also not going to do 20. So 18 says 58.963. Actually, to do this, all we have to do is move the decimal place 1 space to the left. So we're going to get 5.8963 times 10 to the, well, we moved it 1 space, and to get back to 58, we need to multiply by 10, so that's really 10 to the first. And just like when we were dealing with 15 and we had to write 10 to the 0, here we need to write 10 to the first to show that it's 10 to just the first power. And our last example, number 19, says 590. Well, our decimal place is here. We need to move it 2 spaces to get 5.9 times, okay, and this 0 here, we're not going to write anymore, right, because it was after the last digit, the last non-zero digit, and we moved the decimal place 2 places to the left. So to get back to the original, we need to multiply by 10 twice to get back to 590. So 590 is 5.9 times 10 to the second. This one is 5.8963 times 10 to the first. And this decimal up here in 16 was 5.009 times 10 to the negative 7.